This question is an internal resistance question. A dry cell has an EMF E and an internal resistance R and is connected to an external circuit. Okay, so you have a fixed resistor over here. There is current I in the circuit and potential difference across the terminals here. State the expressions in terms of E, V, R and I where appropriate. So if you have a look at these, E is EMF, V is the potential difference across the terminals, R is the internal resistance, and I is the current flowing through the entire circuit. State the total power supplied by the cell. Now, total power equals current times voltage. So we just need to find the current and voltage supplied by the cell, which is the EMF. That is the supplied. So we can simply state that as E and I, because those are the symbols we're allowed to use. Next, the power dissipated in the cell. Now, the power dissipated is the power used inside the cell, which is through this internal resistor here. If it was a perfect cell, then there would be no energy loss. So we're looking at the power dissipated in that resistor. So once again, we need to think about the current and the voltage. Okay, so the current going through it is I, and the voltage going through it is, well, we'll have to use this relationship, V equals IR. And the current going through it is I, and the resistance is small r, which gives us I squared R. 3. The power dissipated in the external circuit. Right, this question, 3, is it's very easy. The answer is very easy, but the idea behind it is a little bit more complicated. Let's have a look at the information that we have here. Okay, we are trying to find the power dissipated here. Okay, but we don't have any information about this resistor. We are given the symbols relating to this. Okay, but the voltage across here, V, is actually equal to the voltage here. And what I'm going to do is I'm quickly going to prove that, even though it's not directly relevant to the question. So what I'm going to do here is a bit of a tangent. Okay? If you're trying to find, let's derive this one here. Let's derive that equation there. This is the energy that, the potential difference, the energy that comes out of the power supply. And that is equal to E, which is the EMF, the energy coming in, minus the energy dissipated inside the resistor. Okay, in there. That gives you V. That's what's actually coming out. Now, you could just think about this, right? If that is the potential difference, the energy per unit charge that is available, and there's only one resistor in the circuit, then all of that energy, V, will be given, in a way, or transferred at this resistor here. So V here is going to be equal to V here. But we can also derive that. If you think about it like an equation, okay, let's have a look. Let's use Kirchhoff's or Kirchhoff's laws. We have energy in, summation of energy in, so the energy in, which is just the EMF, okay, equal to the potential difference across both resistors. So it would be the potential difference here, IR, plus the potential difference across here, which we're just going to call V. If we rearrange this to make it look similar or the same to this, we'll end up with V equals E minus IR. So here we've proven that you can use the same equation to either find V there or V there. So to cut a long story short, the power is dissipated in the external section here, okay, across this resistor is going to be, once again, remember we're working out power, so we need to do current times voltage. The current is I. What is the voltage? It's V, which happens to be equal to the V that we have to use in the first place. Okay, and it's that. Now B, use your answers to A to derive a relationship between V, E, I and R. And you can do that any number of ways. I've done them above already. Either of these two methods would be okay. But remember that the questions are about power. So let's have a look. The power, the idea behind Kirchhoff's law is that energy in equals energy out. And it's the same. It stands for power as well. So if the power in should equal the power out, because it's the energy per unit time, so it's equivalent. And then, so the power in would be the EMF times the current, okay, which we get from this answer, equals the power across the tiny resistor, the internal resistor, which is here, okay, equals I squared R, plus the power that's dissipated in the final resistor here. Okay, we've got the answer there. So that would be V, okay, times I. Now if we simplify that, as you can see, you've got current in each term. So we can cancel those, 1, 2, 3, and we end up with E equals IR plus V. And we're back to this equation again. Yay. Okay, so the next couple of questions are about the graph. So I'm going to do them now because we've got the graph in front of us. One of them asks for the intercept. So how do we know it's the intercept? Because the question is about find the EMF of the cell. Okay, now if you have to find the EMF, if we look at our internal resistance equation, E equals V plus IR. Okay, but that's not really relevant to our graph, because what have we got on our graph? We've got on the x-axis current, and on the y-axis we've got voltage. So let's rearrange that so that voltage is the subject of the equation. So we have V equals E minus IR. Okay, so if we linearize that, Y equals mx plus c. Okay, and now we've got V on the y-axis, we've got I on the x-axis, and you can see that our intercept will be the EMF, okay, so plus C, and our gradient will give us the resistance. Okay, so let's work out the intercept first. If we have a look at the intercept where x equals 0, we get a value of 1.5. Check the units to make sure there isn't any times 10 to the power of anything. So it's just 1.5 volts, which is excellent. The next part of the second question on the next page asks for something a little bit trickier. Okay, it's a bit of a rare question. And it says, find the current when the resistance, the external resistor, is very small. And what it means, it's a bit sneaky actually, because it doesn't say what it means. What it means is when the resistance tends to 0, or in fact equals 0. Now, there are a couple of ways to think about this. If I draw the circuit for you, okay, the external resistor, PD, would be 0. So that would mean that the V here would also be 0. Okay, we can think of it in terms of V up here. If the external resistor is 0, it would mean that all the energy of the battery would be used and transferred in the internal resistance. Because remember, voltage in series is shared. So you would have voltage here and voltage here, split. But if this is 0, then you would have nothing here and all of it here. So that would mean that E minus IR would equal 0. So that means that V equals 0. So this is a really long-winded way of asking what would happen to I if V is equal to 0. Okay, it's a very rare question and a bit of a mean one, but hopefully if you've done it once, you'll remember. So let's have a look. I'm going to extend the line to try and see where it hits the x-axis. Okay, and as you can see, there's an intercept there that shows it's 1.25 approximately amps. Okay, the mark scheme does state that it's 1.3. Okay, and that's to do with the significant figures, but then it uses the value of 1.25 for the next part of the question, so I think that's a little bit unfair. 1.25 amps is okay. Going back to the third part of that question, which is a little bit more traditional, is finding the internal resistance. As we've already said, the internal resistance is the gradient of the graph. So it's important that you write down the read-offs so the examiner can see what you're thinking and what you're doing. And we have some read-offs here from 1.5 to 0, because it's just a right-angled triangle, isn't it? So 1.5 minus 0 divided by 1.25 minus 0. Okay, now remember this is one of them is minus, so this would give you a minus answer. Okay, which gives you a value of 1.2 ohms. Okay. So moving on to this page, we have these questions which we've already done. Okay, determine the EMF, determine the current when the resistance R is very small, and deduce the internal resistance of the cell. So let's go back to here. Complete the diagram to show the circuit that could be used to obtain the data from which the graph was plotted. So it's exactly the same as the experiment we've done in class. So there's our resistor. Okay, but we would need to vary the current. Okay, so this is our ammeter. Let me sneak it in then while I can. You would need to vary the current flowing through, so you would use an internal. You would use a variable resistor. Okay, and then your voltmeter would be here. Okay, so once again, we're ending with a really easy question at the end. So there's two types of IB questions, ones that get progressively harder. And then you've got this one. The maximum power dissipated in the external circuit occurs when the resistance of the external circuit is the same as the internal resistance of the cell. Now, the internal resistance of the cell is 1.2. It's constant, okay? So if the internal resistance is 1.2, and the external resistance is 1.2, calculate the maximum power dissipated in the external circuit. Well, what other information did we get from the graph? We also got from the graph that the EMF is equal to 1.5 volts. So we have the voltage and the resistance. Now this will allow us to work out the current flowing through the external resistor. Okay, so if I draw out the circuit, okay, if we know that the total resistance of both of these together is 1.2 plus 1.2, how do we know that? Because the internal resistance R equals the external resistance, put an ohm there. Okay, so we know the total resistance, RT, we know the EMF supplied, which is 1.5, so that would give us the current. Well, if we just work it out, I equals V over R, total. which is equal to 1.5 over 2.4, which gives us 0.63 amps. That's the current. We're not quite there yet. Okay, if we now know the current that's flowing through the circuit, we know how much current is flowing through this resistor, and now we need to work out the power. So if you can think of a formula that has resistance, 1.2 ohms, okay, and current, we're good to go. And luckily there is one. Power equals I squared R. Okay, and if you substitute the values in, you should get 0.48 watts. Done.